Basic applications of substitution. Welcome to this section on basic applications of substitution. In the previous part of the tutorial, we spent time building up the why behind the change of variable formula, understanding the theory of how it works. Now we're going to shift gears and focus on the how, the practical application of this method to actually solve integrals. Think of it this way: we've got the tools, now we're going to start building something with them. The main idea behind substitution is to take an integral that looks complicated, maybe a bit messy, and transform it into a simpler form, a standard form that we already know how to integrate. We've spent time learning how to integrate basic functions like sine, cosine, exponential functions, and so on. Substitution helps us rewrite more complex integrals so we can use those basic integration rules. In this tutorial, we'll be concentrating on two very common situations where substitution is particularly useful. First, we'll look at integrals where the argument, the expression inside a function, is a linear expression. For example, something like 3x plus 2. And second, we'll tackle integrals with simple polynomial arguments, like x squared or x cubed. We'll see how to identify these cases and apply the substitution technique effectively. So let's get started with the first scenario, linear arguments. Okay, so let's move on to applying what we've learned. Integration with linear arguments. Okay, so let's move on to the first specific technique within substitution. As we discussed on the previous slides, the goal of substitution is to simplify integrals. This slide focuses on a very common and straightforward scenario, dealing with what we call a linear argument. Now, what is a linear argument? It simply means that within your integral, you have the variable x appearing inside a first-degree polynomial. Think of a straight line equation. The general form of this linear expression is mx plus c, where m and c are just constant numbers. So, m and c don't change, they're fixed values. When you spot a linear expression like this inside your integral, perhaps as the argument of a trigonometric function or within a function, the most effective approach is to substitute the entire linear expression with a new variable. We typically use t for this new variable, but you could use any letter really. Here's the general rule, and this is important to remember. If your integral contains a function of mx plus c, then we let t equal mx plus c. Now, this is where a little calculus comes in. To change our variable from x to t, we need to account for how t changes as x changes. So, we differentiate both sides of the equation t equals mx plus c with respect to x. Differentiating t with respect to x gives us dt by dx equals m. In other words, the rate of change of t with respect to x is simply m, but we need dx in terms of dt to actually perform the integration. So, rearranging that equation, we get dx equals 1 over m dt. This is a crucial step. It tells us how a small change in x relates to a small change in t. We'll see this in action on the next slide with a concrete example where we'll apply this rule step by step. Remember, this dx equals 1 over m dt is the key to changing the variable of integration. Example 1. Evaluating \int cos 3x dx. First, step 1 is to identify the linear argument. What does that mean? Well, a linear argument is simply an expression inside a function that's a first-degree polynomial, something like x plus c, where m and c are constants. In our case, the argument of the cosine function is 3x. This is clearly a linear expression because it's just a constant, 3, multiplied by our variable x. Now, step 2 is where we actually perform the substitution. This is the heart of the method. We're going to replace a part of our integral with a new variable. To make things cleaner, let's set t equal to 3x. So, we're saying t equals 3x. This is our substitution. Finally, step 3 is crucial. We need to find the relationship between dx and dt. Remember, we're changing variables, so we need to account for that in our integral. We do this using a little calculus. We differentiate both sides of our substitution equation, equals 3x, with respect to x. So, dt by dx, that's the derivative of t with respect to x, is equal to 3. Now, to isolate dx, we rearrange this equation. Dividing both sides by 3, we get dx equals 1/3 dt. This is the key link that allows us to change our integral from being in terms of x to being in terms of t. Okay, let's move on to our first example. As you can see from the slide title, we're going to evaluate the integral of cosine of 3x with respect to x now. Remember from the previous slides, the core idea of substitution is to simplify the integral. Let's break down how we'll do that here. Keep in mind, this dx equals 1/3 dt is essential. We'll use this in the next step to rewrite our integral entirely in terms of t, which will hopefully make it much easier to solve. We're building towards a standard integral form that we already know how to handle. Example 1, continued, substitution and integral. Okay, let's move on to step 4 of our example. Remember, we're trying to evaluate the integral of cosine of 3x with respect to x now that we've made the substitution, letting t equal 3x, and found that dx is equal to 1/3 dt. We can finally substitute those values back into our original integral. So, the integral of cosine of 3x dx becomes the integral of cosine of t multiplied by dt over 3. Think of it as replacing every instance of 3x with t and every dx with 1/3 dt. Now, constants can be pulled out of integrals. Therefore, 1/3 can be taken outside the integral sign. This gives us 1/3 multiplied by the integral of cosine of t dt. That brings us to step 5, integrating using a standard form. You should have memorized or be able to quickly recall that the integral of cosine of t dt is simply sine of t plus the constant of integration. See, therefore, 1/3 multiplied by the integral of cosine of t dt becomes 1/3 sine of t plus c. So, at this stage, we've successfully transformed our original integral into a much simpler form, expressed in terms of t. In the next step, we'll complete the process by substituting back to express our answer in terms of our original variable, x. Example 1, continued, substitute back original variable. This slide details step 6, substitute back the original variable. What this means is, we need to replace every instance of t in our current answer with what t originally was defined as. Remember back in step 2, we defined t as 3 times x or 3x, so we take our integrated result, which is 1/3 sine of t, plus the constant of integration c, and we substitute. Everywhere we see t, we replace it with 3x. This gives us 1/3 sine of 3x, plus c, and that, my friend, is our final answer. Okay, so we've successfully integrated with respect to t, and now we're at the final step of this problem. As you recall from the previous slides, substitution isn't about permanently changing variables. It's a technique to simplify the integral, and then we need to express our answer in terms of the original variable. Now, keep in mind, we'll be seeing similar steps in more complex problems, especially when we move on to polynomial arguments in the next few slides. The key is to remember this final substitution step. It's crucial to get your answer back in a usable form. Integration with polynomial arguments. Okay, so far we've tackled integrals where the inside function was a simple linear expression, like something of the form times x plus c. But what happens when things get a little more complicated? This slide introduces us to dealing with polynomial arguments. Now, instead of a linear expression inside our integral, we might see something like x squared, or x cubed, or even more complex polynomials. The key to successfully using substitution in these cases isn't just any substitution, it's about spotting a specific pattern, a function derivative pair. Think of it as a matching game. What do I mean by that? Well, imagine you have a function, let's call it g of x. This function is inside another function, perhaps it's being squared, or it's the argument of a trigonometric function like sine or cosine. But here's the crucial part. Alongside that g of x, you also see its derivative, g prime of x, multiplied by the rest of the integrand. Now, g prime of x simply means the derivative of the function g of x with respect to x, so if g of x is x squared plus 1, then g prime of x would be 2x. If you spot this pairing, the function g of x inside another function, and its derivative g prime of x multiplied by the rest, that's your signal to make the substitution equals g of x. This will simplify the integral, just like with the linear case, and allow us to transform it into a standard form that we can easily integrate. We'll see this in action on the next slide with a concrete example, but the core idea is to train your eye to recognize this function derivative pairing. It's the secret sauce for handling polynomial arguments effectively. Remember, we're aiming to simplify the integral, and this substitution is a powerful tool to achieve that. Real-world analogy. Okay, let's move on to a helpful way to think about choosing the right substitution. This slide introduces a real-world analogy to make the process a bit more intuitive. Think of this like a lock and key mechanism. Now, in the context of integration, the lock represents the inner function, which we've been calling g of x. So, imagine some function inside another function. That inner function is our lock. And the key is the derivative of that inner function, which we denote as g prime of x. Remember from your calculus, g prime of x simply means the derivative of the function g with respect to x. The crucial point is this: when that derivative, that key, is also present in the integrand, meaning it's part of the integral we're trying to solve, it unlocks the integral. What does that mean? It allows us to simplify the entire expression, transforming it into a standard form that we already know how to integrate. We've been practicing turning complicated integrals into simpler ones, and this lock and key analogy helps visualize how we identify the part that will allow us to do that. We saw this in action with the previous example involving x squared plus 1, and we'll continue to see it as we tackle more complex problems. Keep this analogy in mind, as it's a great way to quickly assess whether substitution is the right approach, and if so, what to substitute. Now, let's solidify this with another example on the next slide. Example 2. Evaluating int 2x sin x2 plus 1 dx. Okay, let's move on to our second example, and we're starting with step 1. As we discussed on the previous slides, the key to successful substitution, especially with polynomial arguments, is identifying the right substitution to make. So, the first thing we need to do is identify the inner function and its derivative within the integral. In this case, looking at the integral, which is the integral of 2x times sine of x squared plus 1, with respect to dx, we can see that the inner function, let's call it g of x, is x squared plus 1. Now, what's the derivative of this inner function? Well, if g of x is x squared plus 1, then g prime of x, that's the notation for the derivative, is 2x. Remember from your calculus rules that the derivative of x squared is 2x, and the derivative of a constant, like 1, is 0. And this is crucial. Notice that 2x is already present in the integrand. That's the part of the integral that's being integrated. This is a really good sign. It tells us that substituting x squared plus 1 with a new variable t will likely simplify the integral significantly. It's like finding the key to unlock the integral, as we discussed with the lock and key analogy. So, this confirms that this is the perfect candidate for substitution. We'll carry this forward into step 2, where we actually perform the substitution. Example 2, continued, perform substitution. Now, step 2 asks us to perform the substitution. This is where we actually replace part of our integral with a new variable. We're going to let t equal x squared plus 1. So, we are defining a new variable t as being equal to x squared plus 1. Remember, t is just a temporary placeholder to simplify things. Next, in step 3, we need to find the differential dt. Now, what does that mean? Well, think of dt as an infinitesimally small change in t. To find it, we need to differentiate t with respect to x. So, we find the derivative of t with respect to x if we differentiate t equals x squared plus 1 with respect to x. We get 2x. That's because the derivative of x squared is 2x, and the derivative of a constant, 1, is 0. So, we write that as dt divided by dx equals 2x, but we don't want just the rate of change, we want dt itself. To get that, we simply multiply both sides of the equation by dx. This gives us dt equals 2x dx. This is a crucial step. It tells us how a small change in t relates to a small change in x. Okay, let's move on to slide 9. As you recall from the previous slides, we were working on the integral of 2x times sine of x squared plus 1. With respect to x, we've already identified that x squared plus 1 is our inner function, and thankfully, its derivative, 2x, was present in the original integral. That's a really good sign. Now, in the next slide, we'll use this relationship, dt equals 2x dx, to actually substitute into our original integral and hopefully simplify it down to something we can easily solve. So, keep this result in mind, as it's the key to unlocking this integral. Example 2, continued, substitute into integral. Okay, let's move on to step 4, and this is where the substitution really starts to pay off. As you can see on the slide, we're now going to substitute into the original integral. Remember, our goal is to transform this integral into something we can easily solve, a standard form integral. Now look closely at the integral we have, the integral of sine of x squared plus 1 multiplied by 2x dx. Notice that we have both 2x and dx appearing together as a product. This is crucial. From step 3, we found that the differential of t with respect to x, which is dt by dx, is equal to 2x dx. That means we can directly replace the entire expression 2x dx within our original integral with simply dt. So the integral of sine of x squared plus 1 multiplied by 2x dx becomes the integral of sine of t dt. See how much simpler that is? We've successfully rewritten the integral entirely in terms of our new variable, t. This is fantastic because we know how to integrate sine of t dt. As we'll see in the next step, it's a standard integral that we've encountered before. This substitution has effectively unlocked the integral, making it solvable. Remember, we'll eventually substitute back to get our answer in terms of x, but for now, we're happy to work with t because it simplifies the integration process. Example 2, continued, integrate using standard form. Okay, let's move on to step 5, and we're continuing our work on example 2, where we were evaluating the integral of 2x times sine of x squared plus 1. With respect to x, as you can see here, we've successfully transformed our integral into a much simpler form. Now, all that's left to do is actually perform the integration. This is where recognizing standard integral forms comes in handy. We know, and you should have this memorized or readily available in a table, that the integral of sine of t, with respect to t, is negative cosine of t, plus a constant of integration, often denoted as c. So, we write that as integral of sine of t dt equals negative cosine of t plus c. Therefore, applying this standard result to our simplified integral, we get negative cosine of t plus c. Remember, c represents an arbitrary constant, and it's crucial to include it in indefinite integrals. Now, this is a good point to pause and reflect. We've done the hard work of substitution, and now we're down to a very straightforward integration step. In the next step, we'll undo our substitution to express the final answer in terms of our original variable, x, but for now, we have our integral evaluated in terms of t. Example 2, continued, substitute back original variable. Okay, let's finish up this problem. We've done all the hard work, and now we just need to express our answer in terms of the original variable, x. So, this is step 6. Substitute back the original variable. As you can see here, we need to replace t with what we originally defined t to be. Remember back in step 2, we said that t equals x squared plus 1. Therefore, we simply substitute x squared plus 1 back in for t in our integrated expression. So, negative cosine of t plus c becomes negative cosine of x squared plus 1 plus c. And that's it. We've successfully evaluated the integral using substitution. Remember, this final step is crucial. We started with an integral in terms of x, and we need to end with an integral in terms of x as well. Now, if you look at the next slide, we'll recap all the key takeaways from these examples so you can solidify your understanding of this technique. We'll also cover some common mistakes to watch out for so you can avoid them in your future calculations. Key takeaways. First point, linear substitution. When you're dealing with an integral that has a linear expression inside, something like mx plus c, where m and c are constants, and you make the substitution t equals mx plus c. Remember this. It always introduces a constant factor of 1 over m in your final answer. We saw this in our first example with the cosine of 3x. Because of the 3 multiplying the x inside the cosine, we ended up with a 1/3 in front of the sign of 3x plus c. It's a very common pattern, so keep that in mind. Next, polynomial substitution. This is where things get a little more strategic. The key here is to look for a function derivative pair. Essentially, if you see a polynomial inside another function, see if you also see the derivative of that polynomial multiplying the rest of the integrand. For example, if you see x to the power of n, keep an eye out for x to the power of n minus 1. That's a strong indicator that substitution will work nicely, as we demonstrated with the sign of x squared plus 1. Now, the goal. What are we trying to achieve with substitution? The objective isn't just to manipulate the integral, it's to transform it into a standard form. By standard form, I mean an integral that you already know how to solve, something like the integral of sine t with respect to t, or the integral of e to the power of t with respect to t. Once you get it into that form, you can apply the standard integration rules we've already covered. And finally, the final step. This is crucial and a common mistake students make. After you've integrated with respect to t, you must substitute the original variable x back into the expression. Remember, t is just a dummy variable we use to simplify the integral. Your final answer must be expressed in terms of x. Don't leave your answer as a function of t. Always switch back to x. Okay, let's recap what we've learned about substitution. This slide summarizes the key takeaways to help solidify your understanding. So, those are the key takeaways. Keep these points in mind as you practice more substitution problems, and you'll become much more comfortable with this powerful integration technique. On the next slide, we'll look at some common mistakes to avoid so you can proactively prevent those errors from creeping into your work. Common mistakes to avoid. Okay, let's move on to the final slide, which highlights some common pitfalls to avoid when using substitution. This is really important, because even if you understand the method of substitution, these little mistakes can easily trip you up. 1. Forgetting the differential dx. A very frequent error students make is this. They correctly substitute u or t for a part of the integrand, but then they completely forget to also change dx to dt. Remember, when you change variables, everything needs to be expressed in terms of the new variable. You're essentially changing your world from x to t, and you can't integrate a function of t with respect to x. That just doesn't make sense mathematically. You must express the integral entirely in terms of t before you integrate. 2. Ignoring the constant. This one specifically comes up with linear substitutions, like the one we did with cosine of 3x when you have an integral with a linear argument, say, something like integral cosine of x plus c dx, and you substitute equals mx plus c. You must remember to account for the m when you find dt. We found that dt equals m dx, which means dx equals 1 over m dt. Students often forget to include that 1 over m as a constant factor in front of the integral. So, writing integral cosine of 3x dx equals sine of 3x plus c is incorrect. The correct answer is 1/3 sine of 3x plus c. That constant factor is crucial. 3. Incorrect substitution choice. This is about identifying what to substitute. A common mistake is trying to substitute the outer function instead of the inner one. Think of it like this. You want to substitute the expression that's inside another operation. For example, if you have a function inside a square root, or inside a trigonometric function like sine or cosine or raised to a power, that's what you should substitute. Don't try to substitute the entire outer function. Focus on the inner part. 4. Stopping too early. This is a simple but surprisingly common mistake. After you've integrated with respect to t and found your answer in terms of t, you must substitute the original x values back into the final answer. The question was originally asked in terms of x, so your final answer must also be in terms of x. It's like solving a puzzle. You might do some work in a different space, but you need to bring the solution back to the original context. So, keep these 4 points in mind as you practice, and you'll be well on your way to mastering substitution. Are there any questions about these common mistakes before we wrap up this section?